In section 4.4, we'll be talking about the transpose of a matrix. Let's first define this in section 4.4.1. Let A be the matrix, the m by n matrix with entries A, I, J. The transpose AT of A is it's going to be an n by m matrix. So the number of columns and rows is switched from what A had, and we will be switching I and J to. And so this means that the rows of AT are the columns of A and the columns of AT are the rows of A. Let's do an example. So if this is A and I want to look at AT, well, this one is a 2 by 3, so I'll have a 3 by 2. So I'm going to have something of that shape. And this first column here, this first row, sorry, it's going to become my first column. And the second row will become my second column. And so I'll have 3, 5, minus 2. That's it. All right, so we're flipping the matrix. Here are the properties of the transpose. If A and B are matrices and K is a real number, the following hold whenever it's defined, so whenever A and B have compatible size. If I take the transpose twice, well, the rows will become columns and come row again, so I'll get just A. If I have the transpose of A plus B, I can transpose A, transpose B separately, then add them, I'll get the same thing. This one's interesting though. If I take the transpose of AB, I'm going to get the transpose of B, transpose of A. So notice here that the order has switched. The A and the B are flipped. All right, and if I multiply A by K, I can multiply it first, then take the transpose, or take the transpose and multiply it. I'll get the same thing. All right, so the only one that's truly interesting is 3, so let's prove that. Um, let's say that I have a matrix A, and let's look at it like we did when we defined the product. So let me put up the rows of A are V1, Vm, and let's say that the columns of B are W1, Wn, just like we did when we defined the product, because we're looking at the product here. So we know that when we multiply AB, we get the matrix VI WJ M cross N. And so if I take the transpose of this, I will get, remember when you take the transpose, you flip the size and you flip I and J. All right, now let's see what happens when I look at this right-hand side of the equation. The transpose of B will be W1 Wn, because the columns of B will become the rows of B transpose, and then the columns of A will be the the columns of A transpose here will be the rows of A, and so I'm getting these VI through VM. So this is the product that I want to take now. Well, if I take this product of matrices, I will be looking at rows here and columns here, and so I am going to get WI dot VJ, and it's going to be an M by N. And now since the dot product is commutative, then these two things are equal. And so yes, indeed, BTAT is AB transpose. Done. All right, now let's try some example of using these properties of transpose. In example 4.4.2, I'm asked to expand and simplify, so I'm going to start with this one. All right, so I'm going to use the property we just proved here, property 3, that tells you that AB transpose is B transpose A transpose. So this holds at this point only for a product of two matrices. So let me write this as A times BC transpose. And now I have a product of two matrices, one that's made up of more complicated things, but it's still a product of two matrices. And so from property 3, I know I can take BC transpose, A transpose, and then I'm going to use property 3 again, and I'm going to switch these C's and B's. And so this is what I get. Notice that from here to here, we switch the order completely. Instead of ABC, now we have CBA. All right, let's try the next one. If we look at what we know about transpose, I'm going to use property 2 here, that the transpose can come in on a sum. So I'm going to get I transpose plus A transpose transpose. All right, let me take a second to figure out what this I transpose is. So I transpose is this. And if you notice, the rows and the columns of I are the same. So when I take the transpose of I, what I'm getting is still this matrix here. Nothing has changed. It doesn't show any sign of being transposed. So this is equal to I again. And so when we take I transpose, we just get I. And now the last part, that's the first property that we've learned. If you take the transpose of the transpose, you just get A back. All right, let's try a more complicated one. I have a complicated product here. There are tons of ways of doing this. You could pull the transpose out completely and then bring it in at the end, but I'm going to bring it into each part. So I'm going to bring this transpose in. So what I'll get is the 2 comes out, so I'll get A transpose B transpose minus I transpose. We just learned that doesn't do anything. I transpose plus B transpose. So really here I'm using two properties. I'm using the one property 2, that if I have a sum, I can bring it in, and property 4 as well that we haven't seen yet, because I'm actually leaving the 2 outside the transpose. That's what property 4 tells me. So this is 2 and 4. And then once I have this, when I have the transpose of a product, I just need to switch and transpose each part. Like we just said, I transpose is just I, and then this stays. A transpose transpose, we saw this in the last problem. That's just A. All right, now we're ready to expand. I'm going to multiply it out. I'm going to get 4 terms like we usually do. Don't forget to put them on the left if they were on the left, on the right if they were on the right. So I'm going to get this. I'm going to get... And then remember, when you multiply by I, it doesn't change the matrix, so this is what I'll get. All right, so here are the two key facts that I want you to remember from these problems. If you transpose a big product, you switch the order of the whole list. So you read it backwards. You go that way. And then the transpose of I is just I.